Hello again. Today we're going to spend time talking about the 7 quality tools. So before I start into that, I just wanted to give a little bit of background. So the 7 quality tools are attributed to a gentleman by the name of Karu Ishikawa. Karu had worked, actually during the Second World War, he had worked for a division of Nissan. And after the war, and in fact, in 1960, he became a professor at the University of Tokyo. And most of his quality work that people are associated with come from that period of time from 1960 on. So, for example, in early 60s, I think it was 62, he comes up with the concept of quality circles, which is one of the key elements that he is known for. And we talked a little bit about it the previous week. He also popularized these 7 quality tools. So he didn't create most of them. In fact, 6 of them pre-existed from other places, and we'll talk about those. He did create the cause and effect of the fishbone because there was a need for a tool to do that purpose that there wasn't kind of one in place already. So he kind of developed that, but that whole space is really attributed to him. So the idea within these quality circles was that the employees would use these tools to manage their own environments that they worked in. So instead of relying on somebody else to be responsible for figuring out what problems there were or how to fix them or whatever, the employees would take responsibility collectively on doing that work themselves, and that's really kind of the key of the quality circle concept. So let's spend a little bit of time and let's go through these 7 quality tools and see what they're about. Okay, so here we go. Interesting that the first slide here, we've got a quote from Deming: "The defects are not free, somebody makes them and gets paid for making them," which is true, right? Not hopefully not intentionally, but it does happen that way. So we're already paying for these mistakes in more ways than one. So here's a quick look at the 7 basic quality tools, right? So process flow, check sheets, cause and effect, or Ishikawa, Pareto, control chart, histograms, and scatter. And we'll quickly go through each one of them. So a flow chart you may have seen before. You may not have seen this variation that we're showing. This is actually in a swim lane configuration. And this is where this particular variation of it breaks up the various different tasks or activities or things that happen into various different departments. So it's a way of layering on top of an existing flow chart, kind of who's responsible for these particular pieces. It's all about mapping a particular process. So you would do it to create a process. Very commonly what happens is before you start a process improvement initiative, what you would do is you would look at the relevant processes for that area, and you would flow chart them to see what that behavior looks like today. And a lot of the first work that you would do at improvement is you would actually take a look at that base flow chart and you would work through and go, well, what would I do differently? Where are there opportunities for improvement? So quickly, on the example that's here on the page, almost all of the activities seem to take place between the folks that are responsible for contract management and or lawyers. And this is just to get to the point where they're actually going to pick and ship the order. Excuse me. So 2 things jump out at me looking at this. So one of them is customer submits a purchase order and the sales rep just puts it into the system. If all they're doing is entering the information, I'm not sure that there's any value in the step. It probably would be a lot better and a lot easier process if you had an online tool that the customer could directly put their orders in. Now, if the sales rep takes the orders from the customer and there is some interaction from them, so they might look and go, oh, well, I see you've ordered 4 of these. We have this in a 6-pack, and if you buy the 6-pack, it's actually this much less per one, and so on and so forth. And if there's that kind of an activity, obviously there may be some value in that interchange. But if it strictly is they're basically typing it into a system, there's not a lot of value here. So in fact, one of the things you could look at in a to-be kind of improved process is actually eliminating this step and having customers put it in directly. Another one is if you look at this contracts approval step, so basically if there's anything that's outside of the standard terms, it gets kicked to lawyers that look at whether changes are okay, and then you get into this whole cycle, and Lord knows how long this takes. But I know in in my experience, anytime you got to go to lawyers to make changes to any kind of standard terms, it takes quite a lot, quite a long time before you can work it through. So a couple of things. So one of them would be, how often do you get this that happens? So how often are there non-standard terms? If it's, 2% of the time, it may not be worth doing anything about. If it's 15% of the time or above, I'd say there definitely is something that's worth doing about that. And you may look at changes in your process itself. So for example, why are we waiting till we actually get an order to do this contract review process? Why not do it when you set the customer account up, and then you don't necessarily have to revisit it? And then in fact, that's not necessarily part of that process. So there's just a couple of thoughts around that particular example, and that gives you an idea kind of how you would use that tool. So next one we'll look at quickly is a check sheet. So a check sheet is a really low tech but very, very useful way to gather information systematically. So often what happens is we may have, we may think that we're seeing some particular issues, but with lack of, specific data that's telling us that that's true or not, we don't really know, right? So maybe I work at a motor assembly place, and maybe I'm Lester here that's on the check sheet, and it's kind of like, yeah, I think we're seeing like a lot of problems with parts. Okay, well, just because you think there is, maybe there isn't. I mean, you can't do this based on spec. You need data, and you may not have been gathering this data. So check sheets are a really easy way to be able to do that. So what happens is, in this case, so they issue this out. They do one of these a week per employee. All they do is put a check mark every time they run into one of the particular issues that they see. And you would work through this process, because you'd have to figure out, well, what defect types do we tend to see? So what's going to be on the list? And so you spend a little bit of time figuring out what that tool looks like. And then you would use it over a period of time, and anybody else in that space would use it over a period of time. And then the data from that is used to help analyze what's going on. So often what happens is check sheet data then goes into another tool. So often you go from check sheet to Pareto, for example, and we'll talk about Pareto later. In this case, if just looking at this single one, right, one of the things you're looking for is patterns, and one of the key things in problem solving, particularly in quality spaces, is you're looking for the biggest bang for your buck. So what's my biggest problem? Because in a lot of cases, the effort and the process behind fixing a problem, or at least from the identification of it can be similar. So you want to go after the things that'll give you the most value. So just quickly looking at this, there are a variety of issues that they see. The biggest single issue they see are rust on some of the parts. Okay, so I mean, I can quickly tell without having to use a Pareto that that's going to be one of the biggest things to deal with. If you have all kinds of inputs and you have multiple sheets from multiple people over a variety of period of time, it can be difficult to see those patterns, and that's when something like a Pareto becomes very powerful. In any case, the other thing that I find interesting is, so if I look at this, the issue is the biggest on Monday, and then it progressively gets better as the week goes on. And I'm assuming Saturday and Sunday they don't work because they're not showing any errors on either of the two, but there's no errors on Friday, right? But Monday have the most. Why is that pattern like that, right? And that's part of what this kind of stuff is supposed to do, is to cause you to go, hang on a second, why does that look like that? What does that behavior potentially tell me about what's going on, right? So why does it progress that way? Now, I would want to look at previous week and past week and see if is it an anomaly, or is it actually a pattern that's there? If it is actually a pattern that's there, you'd start looking at things, right? So top of my head, if that pattern is valid, one of my suspicions would be something to do with the way the parts are stored. And what's happening is that over Saturday and Sunday, for example, they're gaining surface rust on them. And you would take parts off of a skid. You take the outside parts off first, not the inside ones. And it's the outside ones that would be exposed to the elements the most. So therefore, it likely would be those that would be exposed to the rust the most, right? Maybe that's a plausible solution. In which case, if that's potentially it, then you start looking at, conditions to store things in, or is there a coating that could be put on the parts that would prevent the rust from happening, or there's all kinds of other solutions you can look at. Okay, but that's a quick look at the check sheet. The next one is the cause and effect, or Ishikawa. And Ishikawa is meant for when you get to the point where you know what the issue is, but you just don't know what's causing it. Because what you want to go after is root cause, not symptoms. So with an Ishikawa, you start at the head and you put in the problem. So in this case, like, why is a metallic substance in a product? Because presumably it's not supposed to be there, right? And then you start looking at, well, what might be causing it? And there's a particular methodology. So this one's the 6 M's, which is machines, methods, measurement, materials, manpower, Mother Nature, right? There's other variations of Ishikawas depending on what you're looking at. There's different ones for services, but it's a similar ideology that you're looking at in each of those branches, what in this branch might be causing it, right? So from a machine standpoint, it could be, plating or rust coming off some of the things. It could have to do with fasteners. What's, from a method standpoint, what might be causing it? Maybe there's an incorrect inspection procedure. For measurement, maybe there's a sensor issue. Materials, maybe there's issues with the materials, like in the facility itself, right? Maybe there's stuff coming off the ceiling beam that's getting into it. Maybe there's something with the way people are doing their jobs. And then Mother Nature is often the ones that, so for example, if I'm doing things outside, right? So I can't control the weather. If you are doing things in a part of the world that has a seasonal pattern, right? So that could also affect things. And what you're trying to do with the cause and effect is figure out all the potential causes of what might be happening. And then ultimately you'll work through and you'll look at, are they controllable? Can I experiment for control, or are they noise elements? And if you look at I've put a video link in the weekly materials that if you look at, they go through an example in more depth with cause and effect, and gives you I think a good overview of what the tool is primarily used for. Next one is the Pareto. So Vilfredo Pareto was an Italian economist who was studying the political economy of Italy and came across this observation that 80% of the wealth was owned by 20% of the population. And subsequently, since then, this 80-20 rule, which you may have heard of before, seems to have been applied in an awful lot of areas, right? Where you're often seeing 80% of an effect by 20% of the causes. And that's in fact the Duran variation of Pareto. So where does this apply, right, with quality? Well, one of the things I said before is what you want to do when you're solving issues is you want to solve the big ones first. Well, how do you know which ones are the big ones? Well, you have to figure out which ones are causing the most variation, because you'll always have some things that are going on, and some of them are noise, frankly. And what we need to be able to do is separate out the trivial many from the vital few. And that's the concept of the Pareto. So you would take data from, usually would only have to Pareto if you had data coming from multiple different sources, and it wasn't clear what the pattern looked like. So lots of different check sheets or lots of other data sources from within systems. And what you're looking at is, how often are we seeing issues for a particular thing? And then when you chart your Pareto, you do it based on the frequency of occurrence, and then you rank order it so that, on the left-hand side are the most frequent occurrence, and then tailing down towards the right. And what you want to focus on is those handful of ones on the left-hand side that cause the vast majority, or in fact 80% of the errors. So in the example that's here, looks like for a web page of some sort. There's a bunch of things that are potential issues, but broken links, spelling errors, and missing a title tag is 80% of all of the problems that they see. So fix those 3 things, right? And you improve the quality of that website by 80%. And in fact, a lot of the other things may be anomalies or one-offs, right? So Pareto helps you figure out what to focus on. Control chart. So we talked briefly when we did Walter Schruert. So a control chart, and there's a bunch of different variations of control charts, but basically it's a way to look at behaviors over time. And the characteristics of the control chart is that you have a center line, which is kind of what your intended or your goal of the measurement. So if you're looking at physical dimensions, That's what the physical dimension is supposed to be of an item. And then you have an upper and a lower control limit, which gives you a definition of how much variation is acceptable. And so much of that has to do with the specific tolerances of any particular process. It's normal to see variation around the center line. And in fact, you'll often see patterns of that variation. When the pattern changes, that's often a sign that something might have changed that may in fact cause a situation where you would actually go out of control. And out of control is when you break an upper or lower control limit. So a control chart can give you early warning before you actually have an error, just when you have a change in that pattern, right? And if you see a particular, so the pattern that we see at the moment looks fairly randomized. But if it continued to go with points that were more towards the upside, you go, hang on a second, why am I seeing that pattern differently? What changed at 0.9 or just past 0.9, right? What changed at that point going forward, right? Was it a new shift? Was it something from a new supplier, new training, a new machine? What changed? Because you want to control for the change, because that potentially may create a situation where you actually end up out of control. Next one, histogram. So histograms are, as you can see, they look like a bar chart, but they're designed to look at the distribution of data. So, and histograms let you see distribution data that doesn't follow a traditional simple bell curve, right? So you're probably familiar with the bell curve kind of structure where you have your average in the center, right? And then how tight or how flat has a lot to do with what the tolerances of a process. If you remember back one of the previous presentations, there was a picture of two basically curve diagrams for warranty costs for transmissions from American and Japanese vehicles, and then the tolerances of the processes, and that basically kind of shows you the underlying parts of a histogram. So this particular one, right, you see there's two peaks. So histogram can show left skew, right skew, multiple peaks. It can show a bunch of different patterns. And again, what you're trying to do is you're trying to display the information that you've gathered in different ways to create new understandings of the information, right? So in this case, if I was building something and the expected length of the item was supposed to be, let's say 6 millimeters, and you had a tolerance 1 millimeter plus or minus, right? So it's supposed to be 6. It'll work if it's 5. It'll work if it's 7, but outside of that range doesn't work too well. And I saw this kind of a distribution. You go, hang on a second. Why am I seeing two, both upper and lower, and I'm not seeing so much in the middle part, right? One potential explanation could be if the process that cuts this part, right, the cutting machine, if it's loose or there's something loose in it, there may be a tendency for it to, in that looseness, kind of bang up against one end or the other, which is causing you to cut parts that are actually either too short or too long. And that variance may be a result of something that's loose. That's just a theory, right? But you would look at patterns and you go, is this a pattern that I expect to see? If I don't expect to see it, what does that pattern tell me about what's going on? And then based on that, what kind of things would I do to start to look at potential causes, right? So I may see this and I'm not sure what it is, and I may go from this to a Nishikawa. So, why are whatever percentage of parts not 6 millimeters in length? A certain percentage of them tend to be less, another percentage tends to be more. And you start looking at why could that be? Could it be this? Could it be this? Could it be this? Right? So, and that's something you'll find commonly between all of the quality tools is that you'll often go from one to another with the same data, and using the tool and displaying it gives you new insights into the same patterns. So the last one we're going to look at is a scatter. So a scatter diagram is not about causation. So it's not about one thing causing another thing. It's about understanding a potential relationship between two sets of data. And why that's potentially important, because if there's a relationship between X and Y, and you understand the relationship between them, if you can control for one, there's a good chance you can control for the other. Or based on one, I can predict the other. And that could have a very important outcome. Now, scatter can show multiple different patterns at different points in the diagram. The patterns may be different. So for example, the example that's here shows the average annual global temperatures. You've got the temperature scale right on the left, and along the bottom, the time period. If you look from the beginning of the data from 1880 to about 1900, there's a fair bit of variation. The correlation isn't very tight, and there doesn't seem to be much of a relationship between a rise in the annual temperature and the time period changing. Doesn't seem to be a pattern there. Once you get past looking about 1910-ish, certainly into 1920, one of the things that happens between 1920 and 1940 is that the pattern gets tighter. So you notice the points get closer together. There's a higher correlation between them. And there starts to be an upward pattern to it. So in other words, as time is going on, the temperature is going up. After 1940 till about 1980, it's anybody's guess, right? It bounces around, there's not a strong correlation, and there doesn't seem to be a strong pattern to it. But from 1980 on, not only does the pattern get tighter, but it also continues to rise, right? So that as the time goes on, the temperature goes up. So understanding the pattern and where it is, as I said, if you could control for one, you potentially could control for the other. The other part is, if I know what one of them is, then I could potentially predict what the other is. And based on that, you can do predictive modeling to figure out what you need to do at any particular point in time. Okay?